Unit 6, Part 4. So we've just finished talking about logical equivalence, right? Two statement forms are logically equivalent just in case they have identical truth table columns under their major operator in their joint truth table, right? We saw an example of that, right? We tested not brackets P and Q, and also not P or not Q. They had identical truth table columns under the major operators. They are logically equivalent, right? So the image you associate is something like this. This is a tree, TTFT, TTFT. Doesn't have to be that exactly, but just same, right? 1 and 2, the two statement forms, statement 1 and statement 2. These would represent the columns under the major operator. They're identical, okay? So logical equivalence, as I said, that's the relation between, on the bottom half of the inside cover of your book, the relation between each pair of statements separated by the two double dots. The left-hand side, the formula on the left-hand side and the formula on the right-hand side stand in a relation of logical equivalence to one another, okay? And because they stand in a relation of logical equivalence to one another, so whenever the first is true, the second is true. Whenever the first is false, the second is false, right? That means whatever the truth value of the first is, the truth value of the second has the same truth value. Because of that, those rules we're going to be allowed to, we're going to be able to use on subformulas, which it's not going to be true for the rules of inference. Two things are true of the rules on the bottom half of your inside cover, the replacement rules, which aren't true of the rules of inference. They are, you can use those rules on subformulas, right? You can use those rules on parts of formulas to replace, if say you've got a conditional and the consequent is the form of the left-hand side of one of those rules, you can replace that consequent of the conditional with the right-hand side of one of those rules, right? You can replace a subformula that fits one form with its equivalent form, right? Because the only thing that goes into determining the truth value of, in this case, that conditional overall, is the truth value of that component, and that truth value is the same in a relation of logical equivalence, right? You're replacing, it's something, I said the consequent of the conditional, that's what you're replacing, right? So it's something hook, say T, where you're replacing with another form, which is also T, whenever the first is T, right? Because the truth values are the same. Also, in the second thing you can do with the replacement rules is if you have an instance of the right-hand side, you can replace it with an instance of the left-hand side. I say those two things now because it'll be good to have them in mind for logical implication. I'll tell you about what logical implication is, and you'll understand eventually, probably not till the end of Unit 8, but you'll understand why you can't do those things for the rules on the inside, the top half of your inside cover, the rules of inference. You're not allowed to do those things because they stand in a weaker relation of logical implication. Right? Logical equivalence is the stronger relation, identical truth tables. You don't have that with logical implication. What is logical implication? Okay, that was the image for logical equivalence. Sorry, that's incredibly. Okay. Statement 1 logically implies statement 2, right? So again, like you'll see, we put 1 and 2 up over the major operators when we do an example of this. I'm going to start with 4b in a moment. But the 1 and 2 here stand for the columns under the major operators of whatever these formulas are. But Formula 1, so this is the hardest notion, Formula 1, this formula, the first formula, 1, does imply 2 when you don't have any rows where the first one is true and the second one is false. So the image you want to have says no true going to false. Okay, there's a lot of questions, the study questions and the first exercises, answer all them, especially with regard to logical implication, to make sure you get clear on this concept and especially how it applies in specific questions, right? The first formula does logically imply the second one whenever you don't have any instances, any rows, where the first one is true and the second one is false, right? Now, what is logical implication? Logical implication, this is made especially clear in section 3, when they're talking about the relation of these relations, logical implication, logical equivalence, to the rules in Unit 7 and 8, as I've been doing. Logical implication is a rule of truth preservation, right? Something one does logically imply two, just in case, right? Just in case is biconditional, just in case just means whenever, whenever it is so, or whatever. Excuse me. If the first formula does logically imply the second, if you don't have any cases of true going to false, right? Because what I'm telling you and I'm saying we don't have any instances of going from true to false, it means the inference is that the move from 1 to 2 is truth preserving. It means whenever the first one is true, the second one is also true, right? Whenever the first one is true, the second one is also true. Okay, so just an easy example. One of the rules of inference on the inside cover of your book is a rule called simplification, right? We're going to call it simp. And it's this rule, right? If I give you a conjunction, you're entitled to infer the left-hand conjunct. You're also entitled to infer the right-hand conjunct. You can also do P, right, by the rule of simplification, right? Now, this is a rule of inference, right? Because what it says is, it says whenever this is true, whenever I give you any conjunction, remember, this is a form, this is a statement form, right? P and Q, take a substitution, instances any statements, no matter how complex. So the rule says, say it formally like this, grasp it formally like this. The rule says, given any conjunction, you're entitled to infer, via this rule, one of the conjuncts by itself. If I give you P and Q, you're entitled to infer P. Now, why is that a rule of inference? It's truth preserving, right? It's truth preserving. It should be very obvious to you that whenever P and Q is true, P is also true. There's no possibility of P and Q being true and they're not being true. Why? Because the truth table for P and Q, the simple meaning of the word and, is both of these things are true. So of course you're entitled to infer that one of them is true, right? So this is a rule. The relation between the premise and the conclusion of this rule is a relation of logical implication. There are no instances where the first one is true and the second one is not true. Notice that this relation is different to logical equivalence. Logical equivalence is a symmetrical relation. If 1 is logically equivalent to 2, of course 2 is logically equivalent to 1. Because if 1 is logically equivalent to 2, their truth tables are identical as a definition. So if the truth table is identical, they're identical, which means 2 is also logically equivalent to 1. Now here, the premise does logically imply the conclusion, but the conclusion certainly does not logically imply the premise, right? That's why we have the first of the differences between the top half of your inside cover rules and the bottom half ones. The rules of inference, like this, like simp. So first of all, convince yourself what's obviously true. P does not logically imply P or Q. Let P be Dan is Australian. Let Q equals a bomb drops on New York City tomorrow. Okay. Can you infer from the fact that Dan is Australian that both Dan is Australian and a bomb will drop on New York City tomorrow? Is that a valid inference? Is it truth preserving? Thankfully, not. Right? Thankfully, here we have P is true, but P and Q is false, because Q, we very much hope, is false. Right? So it's not truth preserving to go from here to here, which is why you are not allowed to do what I said you could do for the replacement rules. the rules of inference, you cannot go from an instance, so the replacement rules, you could go, I said you could go from an instance at the right-hand side to the left-hand side. Rules of inference, you can't. You have to go from an instance of the premise to, you're entitled to go from an instance, or instances, an instance of the premise, in this one premise rule, to an instance of the conclusion, but you're not allowed to go from an instance of the conclusion to an instance, a substitution instance of the premise. You're not allowed to go from the truth of one conjunct to the truth of a conjunction. Not allowed. For good reason. It's not truth preserving. That is, it's possible for P to be true and P and Q to be false, as the Danny's Australian Bomber New York City example shows. Okay? But nonetheless, continue in the next part.